In this problem, we're going to look at the motion of a reciprocating pump located in the center of a beam. We're going to see that it looks like an undamped 1 degree of freedom system with a prescribed force acting on it. But we're going to see that based on the description, it seems like a pretty easy problem to get into, but we're going to see there's a lot of nuance to it that we do have to account for, and we're going to be making some important assumptions along the way that's going to change how we're going to be analyzing this beam. So we want to start with the model of our system, see what this is going to look like. And right away we see here we're going to have the pump, and that is going to be providing a force. So we do have an external forcing happening on this system. The pump itself has a weight of 150 pounds, and then the beam we're going to allow to deform, so that is going to allow vertical motion of the pump as the reciprocating motor is going back and forth. So the deformability of the beam is going to act like a spring as it's able to absorb energy and then release energy. So it's going to act like a stiff spring that allows it to move up and down. So in our model here, where we want to get to is going to be a spring mass system that has some equivalent K and some equivalent M. And we're also going to have the external forcing acting on it. So we're going to have some F of t acting on it, which actually we're given in this. And we are going to be tracking some coordinate x. Now again, really what are we tracking this in our actual system is going to be x. What is the motion of the center, the vertical motion of the center of this beam? And now we would have to arrive at this a little bit more organically if we didn't know up front this was going to be an undamped forced system. But what we are going to be assuming here is that there is no damping taking place. So potentially there should be energy dissipation from the beam itself. It's not just storing and releasing energy. Some energy is going to be dissipated through heat or sound, things like that, friction. But we are not going to take that into account. And really for the most part in this course, we're not going to be compensating for dissipation of deformable objects. It's going to be really tricky to model, or at least model with some degree of accuracy. So we're going to say that the beam here is going to have a stiffness to it, so that's going to factor into the K, the equivalent spring constant. In fact, in this system, we'll see it's the only thing that has stiffness to it. And then looking at the equivalent mass, well, the pump has a given weight. We'll have to find the mass of the pump itself. And really, the beam, since it's made of this A36 steel, also has mass in our system. For this first version of the problem, we are going to ignore the mass of the beam itself. We're going to revisit this at the end of the section, and we're going to see that we really do need to compensate for the mass of this beam or this plate because it does have a lot of equivalent mass. However, accounting for the mass in a deformable object or a distributed object is going to be a little bit trickier, have its own calculations involved, relative to the pump itself can just behave like a point mass because it's not deforming, it's just going to be moving up and down. So the mass, we could start with the mass or the spring constant. Again, there's no damper in this system. We're not accounting for any energy dissipation. So let's look at the mass that's going to go into our spring mass system in the end, which, again, once we compensate for everything, account for everything, we're going to see this is a undamped 1 degree of freedom forced system. All right, so what's the mass? We are given the weight of this reciprocating pump is 150-pound force. But that is a weight, which is a force. It's not a mass. We want to make sure that we are working in the correct units when we are solving for masses versus forces. So typically what we do is we would take the weight of something, 150-pound force, and we would divide by gravity in order to find the appropriate mass. So gravity in English units, 32.2 feet per second squared. Right? And that would give us a unit of slugs. But slugs is going to be based on feet, and And that's not going to be good for this problem, as we're going to see. So actually what we want to do here is we're going to need to convert this, because we don't want this mass in slugs. We want it in another unit. So I'll come back after we look at, say, the stiffness to further justify why we're going to make this conversion. But we actually want to convert this and say that we have 1 foot is 12 inches. I want my base unit in inches, not feet, for this problem. And we're going to see that other things we are going to be measuring are all based in inches, not feet. So in English units, this is going to get a little bit trickier. So what this is going to let us do is I have feet up top, I have a feet down here. So I'm going to have now inches and seconds involved. So going through these steps, I'm going to find that the mass comes out to be 0.388 pound force seconds squared per inch if I work out all the units. And that is going to be also known by a somewhat unofficial term that is 0.388 blobs. Or just simply blob. But the unit is blobs. So kind of a silly sounding name. I don't believe it's an official term, but a blob is it's really the inch version of a slug. Slugs involve feet. That would be pound force seconds squared per foot. This is going to be pound force seconds squared per inch, which we can also call a blob. So it's another unit of mass in the English system, but it's based on inches. And we'll see in a second, why does this help us? Why does this matter? Okay, so since we're ignoring the mass of the beam, the only thing that's going to have mass in this system is the pump. So this is the mass of the pump, which is also going to be our equivalent mass. Now, as a note, we can do this because this mass is located directly on top of the degree of freedom we're trying to track, which is the vertical location of the center of the beam. If the pump were not centered on this beam, then we would have to make some accommodations for that. But here, because the mass is already on top of our degree of freedom, the mass of the pump is actually the same as the equivalent mass in our system. So mass is done for here. And we'll see when we revisit this problem later that we're going to have to make a compensation because the mass of the beam is distributed from all the way to the left to the right. How do we find the equivalent mass located at the center? Now, M is taken care of. Right, so the one trick here was making sure our units are going to be correct. Now, we could have done this in slugs, but we're going to see in a second here why that's not really going to be compatible with the rest of what we're doing in this problem. So now we can look at the equivalent stiffness. All right, so we have the only stiffness we're going to have is due to the bar that is able to deform. Nothing else is going to store potential energy in this system. So we want to find what's the equivalent spring constant of this bar. Now, to do so, we're going to have to look at a couple of things. We have to look at its boundary conditions. On the left, it's built in. On the right, it's built in. And the force in the bar is located directly in the center, or the applied transverse force on the bar is at the center of it. So we have a bar in transverse bending. This is a time that we want to use our beam table to get an end result of the stiffness. So pasting in from the beam table that was shown earlier, or we can look up a standard beam table, this is the situation that we have here. So again, we have to make sure that when we look at the beam table, it matches what we have. This is a fixed beam, and this force P is located at the center of it. So L over 2, L over 2. So this matches the situation we have here. The forcing is at the center of the beam. Everything else is okay. So we want to go and find the equivalent spring constant. So what this has told us is, from the beam table, this is what we could call delta. And delta is the vertical position of the center of the beam. Now, if we were trying to track a different degree of freedom, if we wanted to know what was happening a quarter of the way through the beam or 3/4, this calculation would be different. So just make sure that the delta we're tracking is the same as the degree of freedom we're trying to track in our system. So this PL cubed over 192 EI is always the static deflection at the center of the beam. So that's what we want to use here. So delta is PL cubed over 192 EI. So we can rearrange this because really what we want is the ratio of the force that's being applied to the displacement, because that would be the same as the units that spring constant should be in should be force per unit length. So if we rearrange this to get P over delta, we'll get 192 EI over L cubed. All right, so we're going to need to find a couple of things out about this. So we need to know the Young's modulus for this material. We have A36 steel. So the Young's modulus here that I'm going to use is 30 million psi. So 30 times 10 to the 6th psi. And we just want to recognize again the units that, well, psi is pounds per square inch, but we do want to check our units here, and we'll see why we want our mass expressed as blobs, or pound force second squared per inch. So really this is also a pound force, just to make sure that we are not confusing pound mass here. So 30 million pound force per square inch. So notice in the denominator I have inches, and that is going to interface with the mass in a little bit when I'm looking for all of my common units. All right, so that's the Young's modulus we're going to use for this A36 steel. Now we need to find the area moment of inertia I. All right, so we're given the information about it, that this beam has a thickness of 0.5 inches, and we can see in the picture how thickness is defined. A length from left to right in the picture of 100 inches. So let me just add a cross-sectional picture here of the beam. This is going to be the 0.5 inches. And then we know that this width is the 20 inches. So it is a pretty wide beam that we're dealing with here. So it should be fairly stiff, and we're going to see that also when we revisit it, it has a lot of mass to it as well. So the I we want to use is always going to be based on the neutral axis that we're bending about. So the neutral axis we bend about is going to be this horizontal axis through the beam. So for our I, we have a rectangular cross section. It's going to be 1/12 BH cubed. In this case, the B, the base, is the 20 inches. And the height that gets cubed is the 0.5 inches. So we always cube the dimension that is perpendicular to the neutral axis of bending. And we're going to have a linear term, that's inches, that is parallel to that. Right, so 1/12 20 inches times 0.5 inches cubed, we get an I of about 0.208 inches to the 4th power. All right, so now we can put this together and we can find our equivalent spring constant. So K is going to be this P over delta term. So that's going to be 192 times E, which is 30 million pound force per inch squared, times I, we just found was 0.208 inches to the 4th power, over the length of the beam. That was given to us to be 100 inches. So 100 cubed, inches cubed. And now we can just check to make sure our units are going to be in agreement. I'll just rewrite this, inches cubed. All right, so we have an inches to the 4th. We have an inches squared under this pound force. So I can cancel out that inches, and this becomes 2. So I can do the numeric calculation here. I get 1,200. I'll have pound force on top. I have inches squared on top, inches cubed on the bottom. So I get inches on the bottom. So 1,200 pound force per inch. That is the right unit for this, is force over distance or force over displacement. So an equivalent spring constant of 1,200 pounds per inch. So again, going back to units, Young's moduli are, in English at least, usually given in PSI. So because that was going to be in inches, that's why I'm going to choose to do everything in inches, that mass with blobs, and now the spring constant in pounds per inch rather than like a pound per foot. So I have enough now to go to my equation of motion because I don't have displacement in the system. I now know my equivalent mass, my equivalent spring constant. I was given what the excitation force or that external force was in the system. So now I can put together my equation of motion. So my equation of motion is going to have this mx double dot term plus kx equals f of t. But now let's put in the specifics. So the mass here in blobs, which is pound/second squared per inch, so it's an inch term, I have 0.388 x double dot plus 1,200 x equals, and we were given that forcing 50 cosine 10 pi t pounds. 50 cosine 10 pi t, and that is going to be in, again, pound force. So K is in pound force and inches, and M is in pound force and inches as our units. So this equation of motion here now has all of our units in agreement, which we want to make sure before we go any further that we have everything in the same base unit. Right, so with our equation of motion, we can move on to our identify step. Now, since we're in this subsection talking about undamped 1 degree of freedom force systems, we already do know what it should be, but let's go through and identify. So we are undamped. Looking at that left-hand side, there is no x dot term, so it's an undamped system. We have 1 degree of freedom. X is our only dependent variable. It is linear, which we should include. We have an x double dot and x, but there's no cross terms, nothing is squared, there's no trig terms on the left-hand side. Our dependent variable only is linear. It and its derivatives are linear. Now this is forced because we have a right-hand side that's not zero, but it is simple harmonic forcing. So SH is just for simple harmonic forcing. And we know that because it's just a single cosine term. It's not more exotic like we'll get into in the next section, just simple harmonic forcing. And also specifically, it's cosine. Okay, so with this identified, all of these important features, we now can put together what our x of t is going to look like, and then we're going to have to fill in the gaps. So again, we've already solved every system generically that was undamped 1 degree of freedom linear forced with a cosine on the right-hand side. So we can just put that in. And actually we can go one step further here because our initial conditions are all 0. So that actually can simplify what we have in addition. Now normally we would save the initial condition step for later, but we actually already know this simplified system is going to be this x, I'll put it capital, emphasize that, times the cosine omega t minus cosine omega n t. Right, so because of the 0 initial conditions, we know that it's going to simplify down to this, but we can look at the more general solution. With the system identified, we know that this page contains the solution. Now, in the middle here, we don't need to use this longer form because we already know x dot naught is 0 and x naught is 0. So we can jump right down to the bottom form here, and that's what we are looking at. So this is our x of t. Because we have successfully identified our system, this is what the solution will look like. And now what we're going to have to fill in is we just have to identify our omega n, and x as is defined up here. So let's get some of the parameters we're going to need. Omega n, always a good idea to find the natural frequency, root k over m when we have this 1 degree of freedom system. We've already ensured that our units were all in base units with inches as our base length measurement. So we can find that the natural frequency is going to be 55.6 radians per second. And that's one piece of the puzzle that we need for this full assembly. And our x term. Different ways we can formulate it, but I'll use this f naught over m times omega n minus omega times omega n plus omega. So the omega n we already know, and omega is the driving frequency, which is going to be this 10 pi. 10 pi radians per second is the driving frequency. I'll just make sure that's marked here. So that is the frequency of that external force, is our omega. So coming down here, x is going to be the amplitude of our forcing. That is the 50-pound force. And we have an m of 0.388. Our natural frequency to 3 digits, 55.6 minus 10 pi. And then 55.6 plus 10 pi. As a quick note, I corrected the input frequency omega to 20 pi radians per second. Everywhere here, it should have been 20 pi, not 10 pi. So everything else we did is still okay here. The only thing that changed is our equation of motion is 50 cosine 20 pi. And now our calculation down here for x is going to change a little bit as well. So 55.6 minus 20 pi, 55.6 plus 20 pi. We get an amplitude of negative 0.150 inches. Just to check the units again, the force was given to us in pound force. The mass was in pound force seconds squared per inch. This is in radians per second. This is in radians per second. So we have a second squared cancel there. We have a pound force and a pound force, so we are left with inches. So again, just checking that our units are making sense. And I guess along with the parameters, I just want to explicitly put our omega is 20 pi radians per second. So now we can assemble our full x of t based on the parameters we just found. Now we can skip that initial condition step because in this one our initial conditions were all 0, and that was actually already baked into our x of t. But normally, yes, we would want to find our x naught and our x naught dot, but they were both 0. So putting our x that we just found, negative 0.150 inches, times cosine times our driving frequency, 20 pi t, I'll just leave it as 20 pi, minus cosine of our natural frequency, 55.6 times t. And what we get here is this will track the vertical position of the center of beam at all points in time. So again, notice that our solution, because there's no damping in it, it's going to have the driving frequency and the natural frequency involved. And also what we should note about situations like this where we're starting from rest and we have that form of x times the cosine of omega t minus cosine omega nt as a side piece, we have this amplitude of, well, the magnitude of it is 0.150, but if we look at just this amount inside these parentheses, we just want to think about what range this can have. So assuming that the driving frequency and the natural frequency are not multiples of each other, they're not harmonics of each other, then there eventually is going to be a time t where the first term is going to be at its maximum value. Well, the cosine can be a maximum of 1, minus the second term at some point will be at its minimum value of -1. And then the opposite is going to be true. There's going to be a time where the first cosine term will be at its minimum of -1, and the second will be at its maximum of +1, and we're going to get -2. So this term here, the cosine minus the other cosine, The biggest it can ever be is +2, and the smallest it can ever be is -2. Again, as long as they're not integer multiples of each other in the frequencies, there's some time where one's at the minimum, one's at the maximum, which means that the minimum and maximum of x of t is going to be twice the amplitude. So x of t minimum is going to be -2 times the amplitude of x, and the maximum it will ever be is +2 times that amplitude. Now, when we have initial conditions, it gets more complicated than that. And if it were a sine instead of a cosine, it's more complicated than that. But we do want to remember this, and we can check it when we are looking at what the solution looks like in MATLAB, is that we should expect the maximum is about 0.3, and the minimum is going to be -0.3 based on these values. And this is going to be, again, in inches. Now, we can look in MATLAB and just make sure we are second checking all of the calculations we're making. So we have our Young's modulus, PSI, our moment of inertia, just checking that was calculated correctly, 0.208. Length of 100 inches, how we calculate our K value once we knew E and I and the length. And then all of these other calculations I'll just go along the way here and look at. Just make sure our X is correct, -0.15. And all of that looks good. So what I'm going to do here is I'm going to make the data, because we know what the value of X is going to be, that X of t. So I'm going to do this for 2 seconds and with a time step of 0.01 when I make my function. So let's just see what this looks like. All right, so my t values go from 0.01 seconds to 2 seconds with that same 0.01 in between. This is going to be important because we're going to go one more step in our analysis than simply plotting what the result looks like. But I'm going to now plot this. I have my simplified x of t down here in line 47, so I can make this calculation, and I want to plot it. So when I run this and I plot my results on the bottom subplot here, that's my position. And on the top, just for comparison, I have here the forcing. So that's just that 50 cosine 20 pi t happening here. And on the bottom is what the position is doing. So a couple things to check is, does the maximum and the minimum make sense? My maximum is 0.3. That was to be expected because it's twice the x value of 0.15, and the minimum goes down to also about -0.3. So that also makes sense. And if we see what the response looks like, we do have two frequencies happening here. We have this quicker frequency, and then we have this slower frequency happening as well. So that's what the center of the beam is doing once we start our timer, and that pump instantly gets up to the 20 pi radians per second. And we can look here at the time between peaks in this slow wave that's happening. So one peak, I'll use this one, is at 1.35 seconds and 0.45 seconds. So let's just see what that time difference is. It is 0.9 seconds. And if we convert that to a period, we have 2 pi divided by 0.9 is a 6.98 radian per second angular frequency. And if we take the difference between our natural frequency and our driving frequencies, we're getting 7.2. So our calculation is a little bit off. We are seeing a beat frequency here, and we can see that from the picture. We have this increasing and then almost zero, increasing and then almost zero. So we do have pretty close to that beat frequency. If we had a little bit more detail in our plot, maybe had a smaller time step, we would probably get even closer. But we are seeing a beat frequency very, very close to what should be the calculated one, which is the difference between the natural frequency and the driving frequency. And because they are relatively close, that rule of thumb applies where we would expect to see a beat. So that is happening here. But if we go and look at a power spectral density based on the data points that we generated, so this is just like what we saw in our Fourier series, discrete Fourier series section, I'm going to take the data I just generated and I'm actually going to go backwards and suss out what those key frequencies were. So this is just like what we saw in the discrete Fourier series subsection, but I'm going to look at the data I just generated. So this is what our manual discrete Fourier series looks like, and then the resulting power spectral density. So here we see two clear peaks happening. And if we see where they're located, we have one peak with an x value of 56.55 and another clear peak value at 62.83. And these are in radians per second. So again, what do those correspond to? Well, again, the driving frequency, W, we have to redefine it. We had 20 times pi. So that's the 62.8, and that is that second peak there. And then the natural frequency that we calculated, about 56, that corresponds to the first peak that we're seeing from the power spectral density. And that should be completely expected, because if we look again, how did we create X? Well, X was created in line 47 with those two frequencies. So the power spectral density gives us back what we expect. But if this were actual data we were collecting and we didn't know what were the frequencies, what were the cosine terms that were generating our data, well, from the power spectral density, we could back out that these are the two frequencies at which our data are oscillating in this lower picture. So going back to the work we did by hand, we were able to get our x of t, we plotted it, and we saw that indeed it was vibrating at those two frequencies from the power spectral density. Because the natural frequency and the driving frequency were close within reason, they were within that rule of thumb for seeing beating, and we did see beating in our result. And we calculated that beat frequency and that beat period, and it matched up pretty closely to the difference between the driving frequency and the natural frequency. From the modeling step, again, I'll emphasize what assumptions we made here is that the beam we treated as massless, although in actuality a beam would act like a spring, a damper, and a mass. We are treating it purely like a spring for now. We'll add in mass later, and we will ignore the dissipation. So this became an undamped system because the only thing that could dissipate energy we're ignoring. So we have this external forcing, we have the mass of the pump that we are taking into consideration, and the equivalent spring constant of the beam also being considered here. So for our model, we got our equivalent mass. Here we wanted to be careful in English units that we were working with the correct base units, pound force, seconds, and I chose inches to be my distance base unit. Then the spring constant K also needed to be in inches pound force, and we got that by using the beam table. So looking at the end conditions of our beam were fixed, and where that static mass was being placed, and also where the external force was being applied, in this case the center of the beam, let us relate the displacement at the center of the beam to the force that's being applied to the beam. And that's how we got this K for this degree of freedom for this beam. Then we could assemble our equation of motion, knowing that we had the mass and the spring constant and that external force. Looking at the equation of motion, we could do the identify step and notice that we had no damping by our model, so there's no x dot term. So it's an undamped system, 1 degree of freedom since x is our one dependent variable, and we had forcing on the right-hand side, simple harmonic forcing, specifically a cosine function only. And also important to this one was that we had 0 initial conditions given to us in the problem. So in our identify step, we were able to use this more simplified x of t, where we can already throw out the x naught and x naught dot terms, and we're left with just having to find the amplitude of this, and the driving frequency and the natural frequency. That's what we did in the parameter step, and then put it all together to get our closed form solution for the vertical position of the center point of this beam.